Welcome to Brain Vision.
In this example, we have a balloon filled with helium, and we want to find the absolute pressure of the helium gas such that the balloon is just sitting suspended in air. It's not rising or falling. So we have some parameters here. We have the radius of the balloon, the mass of the material that makes it up, m sub b here, the temperature of the helium gas inside, and then the density of the surrounding air. So there's two things we should think of in this problem right off the bat. Is one, we're dealing with an ideal gas, this helium inside this balloon. So we'll need to recall the ideal gas law, PV equals nRT. And then we're also dealing with a situation of static equilibrium here, where the force of buoyancy on the balloon is matching the force of gravity on the helium and the material inside, or the material that makes up the balloon. So force of gravity. So those two things are matched. So let's actually start with PV equals nRT, and we'll try to solve for what we want, and then we'll see that we need to go to the sum of all forces over here in order to get more information. So if we start with the ideal gas law, we'll take this equation here, and we'll want to solve for P, specifically the pressure of the helium. All these should be for helium, H. All right, so if we divide both sides by V sub H there, we'll have P sub H is equal to NH times R times TH over V sub H. Okay, so what can we figure out right off the bat? Well, the volume of the balloon we can figure out because we know the radius of the balloon is 1.5 meters and it's a spherical balloon. So if you recall from geometry, the volume of a sphere is 4/3 times pi times the radius cubed. So we know our volume. Okay, so that settles that. The temperature of the balloon we sure know, and the number of moles of helium in our balloon is an unknown for us. So let's bust out this second equation here, which is going to come from Newton's second law. So if I were to write Newton's second law for static equilibrium, we'd say the sum of all forces on our balloon is equal to 0. And our forces are the force of gravity pointing upwards, the force of buoyancy pointing upwards, minus the force of gravity pointing downwards. Or another way to write this is the force of buoyancy equals the force of gravity. Now, if you remember, the force of gravity is just going to be mg, right? But in our case, our total mass is the mass of the balloon material plus the mass of the helium inside. So the right hand of our equation is going to be mb plus mh times g. Now the left-hand side, we'll have to remember what the buoyant force is, which is going to be the density of the surrounding medium, air, times the volume displaced, which is just the volume of the helium, or the volume of the balloon, times gravity, g. Okay. So we can see that we have a g on both sides of this equation, so it cancels out. And what are we left with? The mass of the balloon is a known. The mass of the helium is an unknown, in the same way that we don't know the number of moles. The density of the air is known. Yeah, and the volume is known. Okay, so we only have one unknown here. The mass of the helium. And remember, if we have the mass of the helium, we can get the number of moles, right? Because the relationship between mass and moles is just that mass is equal to the number of moles of a substance times its molar mass. So we're going to solve this for the mass of helium, convert it to moles, and then plug everything into our first equation. So if we subtract Mb from both sides here, we'll isolate the mass of helium. So the mass of helium is density of air times the volume of the helium minus the mass of our balloon. And if we calculate that, just using all of our knowns, we should get 13.823 kilograms, the mass of the helium. And remember, for the volume here, we'll have to use 4/3 pi r cubed, where r is 1.5 meters. And now, to get the number of moles, we just take this equation over here, divide both sides by the molar mass, and see that the number of moles is just the mass over the molar mass of helium. And if we do that, we'll have N is equal to M sub H over big M sub H, which I'm going to use 4 grams per mole for this. Or since we want to work in kilograms, we can use 0.004 kilograms per mole. And that's just something we can look up online or in our textbook. And if we do that, we'll end up with 3,455.8 moles of helium. Okay. So now, let's just box that up since we know we're going to need it soon. We have our moles. We have the temperature, the volume, and then R is just a constant. So we are ready to go. So if we plug all of those values in, we get that the final pressure is 6.2 times 10 to the minus fifth, or just 10 to the fifth pascals. Okay. So what we figured out is what the pressure of helium in our spherical balloon needs to be in order for it to be perfectly suspended in static equilibrium in the air.